Yeah. So, welcome everyone to today's session. So, thank you for your reviews and comments in the Zoom. I'll request you to please subscribe on YouTube too. Okay, so without wasting time, let's start it. Okay. Okay. So, I hope I'm audible. Let me check live that if it's everything is going on well. There must be no any technical issues this time. Okay. Yeah. So there must be no any technical issues. Let me check a live session if it's available there. Technical issues this time. Okay. Yeah. There must be no any technical issue. Let me check a live session is available there. Is available there. Yeah, I mean it's good. Okay. So in the last session, we were at, I mean, we have seen force on a mass in a gravitational field. We have seen one formula, 2 gm upon r square phi sine phi by 2. Okay. So now we'll start with, okay, we have also seen gravitational field due to uniform circular ring at a point on the axis. Okay. And it was max at r by root 2. Now we'll see gravitational field due to uniform spherical shell and hollow spheres. Okay. So let's start. If you have any queries, please give the comments. Okay. So at first we'll see what's the gravitational field. Okay. When I say gravitational field, I basically mean that gravitational field intensity, that is E. In some books, you'll find it by E, I mean I. Okay. So symbol which we're using here is E, gravitational field intensity. So do you views? Suppose we are having a hollow sphere. So let me treat it as like hollow sphere. Okay. This is a hollow sphere. And hollow sphere is also known as uniform spherical shell. Okay. Since it's a hollow sphere or a uniform spherical shell, we'll say the mass is only present on the periphery. There's no mass inside in the inside portion, isn't it? So from center to periphery, this is basically radius or radii. Okay, that's fine. So now two cases are occurring. It can be asked to find gravitational field intensity at a distance r, which is basically, let me take a point here, which is an outside point, which is basically an outside point. Okay, outside point. Also, we can be asked to find gravitational field intensity in the inside point. So this r. See, r is a variable, so we can write the same symbol. Okay, this is for inside point, gravitational field intensity. So it can be asked from us for the outside also and for inside also. You need to find it out. Okay. Please try it out. In the Zoom session, students, please try it out. Okay, so I hope you have well tried for this, isn't it? So Ismail, what I want to do is this. First of all, let us find for the inside point. Okay. For the inside point, if you take this dm, for the inside point, if you take this dm, then intensity, let us take for the center, okay? If you take, suppose I take R as 0 or wherever inside. So you will find that whatever the intensity is by 1 dm mass, that is infinitesimally small mass, the gravitational field intensity due to this dm mass, if suppose it is attractive, it's something as E naught here. You will find that due to some other masses which are anti to this, anti means which are opposite to this, somewhere here, they will generate a gravitational field intensity here, which 100% cancels this E naught. So you can think like this, that for the inside portion, for the uniform spherical shell or hollow sphere, the gravitational field intensity always goes to zero. Why? Because there is an anti-effect. It's like the tug of war game. I mean, if you have the colorful, I mean, in the center thing. I mean, if there are two teams, Team A and Team B, if both are applying the same forces, do you think that in between items, whatever the color, green, red, whatever, it will move? Some people they just hang the handkerchief there and then. Do you think it will move? There's a signal, no? I mean, in which direction that colorful thing moves, the team wins. The team wins. If it's not moving, means the team is not winning. Same effect here. Somehow you will find, so this distance is near and that distance is far. How you're saying this? See, that's fine. You know the expression for gravitational field intensity due to dm mass. We know this thing. We know it's dE is equals to G by R square dm. We know this thing. See, remember this. This small gravitational field intensity is not just dependent upon this dm mass only. It's also dependent upon R square. But it's not dependent upon this gravitational, universal gravitational constant, because it is 6.67 minus 11 Newton meter square upon kg square. You know this thing. So it's dependent upon this factor and it's dependent upon this factor. Isn't it cool? So somehow, via decreasing the distance, increasing the mass, or increasing the mass, decreasing the distance, somehow. You can think like this. Here the dm mass is present at small mass, distance is less. Distance is less, this quantity goes up. Distance is more, but more mass is required. So somehow it will cancel each other. I hope you're able to visualize the things, isn't it? So we'll say for the inside point, net gravitational field intensity is equals to 0. Okay, write it down, please. Now we'll check for the outside points. Okay, so I hope you have just written this. Okay, so now we'll check for the outside points. Okay, so for the outside point, if we check, it's again very interesting. See, you have studied the concept of center of mass. Okay, you have studied the concept of center of mass. Okay, center of mass concept you have studied. So we know for the center of mass thing, we can assume that all the mass of this uniform spherical shell or hollow sphere can be supposed to concentrated at the center point. Okay. So the problem now reduces from this to particle problem. That is, Suppose the mass of this complete uniform spherical shell is capital N. So we'll say electric field intensity for outside point is G M, and what's the outside distance? It's R square. Very easy. So you can write it down like this. So this is for outside point. Okay. Inside we know it. Let me write both the things together. So I can say this is for the outside point. So for inside point, this goes to 0. Okay. Please note it down. Now we'll see the graphs. See viewers, this is electric field, this is gravitational field intensity E. This is R, which is a radial distance from the center. And this graph which we are drawing is for the uniform spherical shell hollow sphere. Okay. So we know this thing that for R less than R, gravitational field intensity is equals to 0. Everyone knows this. Okay. For R greater than R, okay, gravitational field intensity is basically G M upon R square. This also we know. If we wanted to find that small r is equals to radius, that is at the periphery points, we'll say r equals to r. Just substitute. You have to just do the substitution. Okay. So we'll say E Gm upon R square. Okay. It's done. Very good. So now let's check out the values. So we see for R up to R, just below, just behind, the values are 0. So we'll say on the x-axis up to R, this much, the gravitational field intensity is 0. Y coordinate is 0 because that y coordinate is for gravitational field intensity. Okay. So we'll say up to this, it is 0. Then suddenly when R is touching the periphery of this uniform spherical shell, it goes Gm by R square. So if we suppose this is something as Gm by R square, let me write it as E naught, or it's better if I write it as ER. ER. So we can say this is our values. Okay. And for other values that is greater than R, this is inversely proportional to R square. Remember, for inversely proportional graph goes like this. Okay. For inversely proportional graph goes like this, parallel to x-axis or parallel to radial line. Okay. So please note it down. It's very important. Okay, so I hope you have noted the things in a very well structured manner. Okay. So now in this, we'll be going towards a uniform sphere. Okay. gravitational field due to uniform solid sphere. We'll check this now. Okay. So see, let me erase this and then I'll explain you in a well, it must be explained in a well manner. Okay. So remember, this is solid sphere. This is what? This is a solid sphere. So now mass density is not just present on the periphery portion. It's not just like a globe on the upper part. It's present inside also. So there is a mass density which is present inside the material. Material is present everywhere. Okay. So now again the three cases arises. See, in this course, which we are not going into the derivations. If it's required, we'll see the derivations. We are directly going towards the formulas. Okay. And I think it's a complete crisp course. So it's good for you. So we'll say at R less than R, that is inside point. We have gravitational field intensity given by the formula. Remember, this is somewhat different. You know, in the uniform spherical shell, it was zero, or hollow sphere, it was zero. Now it's a solid sphere. So we say it's not zero, it's G capital M R upon radius cube. Remember this? G M R upon radius cube. G is the universal gravitational constant. M is the mass of this complete solid sphere. R is the radial distance. So you can say it's like YMX because this is constant, and this is also constant. Since capital R is a radius, it's constant. R into R into R is R cube. That is also constant. Okay. So now if we see R equals to R, that is at R radius, we'll say our answer will be, it's very easy. I mean, so you have to just substitute the values. When I'm going to substitute this R here, again, it's the same thing. That is G M upon R square. Cool. Okay. So we'll say at periphery. When R goes greater than R, when R goes greater than R, so what's the answer will be? What do you think? So again, it's very interesting. I mean, that's the same approach which we have applied for the hollow sphere, uniform spherical shell. For the uniform spherical shell, we know this thing that when the R goes greater than capital R, that is for the outside points, we say it's Gm upon small r square. Because all the mass is supposed to be concentrated at the center point as per the center of mass concept. Okay. So we'll say here, this is Gm upon mass. And this is for outside point. Okay. Please note it down. Okay. So now, dear students, let's start it. So next point which we're going to do is this, will generate the graph of this. So now we are going to generate the graph. This is gravitational field intensity E. This is radial line R. Okay. For r less than r, this is why it makes sense. I've already explained you. I mean, it's already explained to you people. Constant, 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 y, constant, x. Okay, because x is radial line on the x-axis. E is gravitational field intensity on y-axis. Okay, nice. So we'll say up to r equals to r, it goes proportional like this. Okay. After this, for r, it is a constant. We know, everyone knows this. This is E at r, which is equals to. That's the same graph as we have discussed in the previous thing. Okay. So for greater than r, it's again the same line. Something like this. Remember, this is a straight line. This is straight line. Okay. So this ultimately will be parallel to x-axis, which is a radial line. So this is a graph for gravitational field intensity or gravitational field due to uniform solid sphere. Okay, please note it down. Okay, so I hope you have noted all the things, and if time has been provided, it's like a regular class session, which is like the classroom. So you will have provided enough time to write these things. Let me erase this now. Okay, so now let's see one more thing. How can we do the interpretation of acceleration due to gravity in terms of Earth's mass in radius? It's not just about the radius, radial distance. Okay, let's see. So suppose this is Earth. Okay, that's Earth. And there is a mass on the periphery. You must let us take the mass as m naught. Okay, the mass is m naught, and mass of the Earth is capital M. Okay, suppose this is the center of the Earth. The distance between the small m naught mass, which is at the periphery and center of the Earth, is capital R. Okay. Now, if we apply Newton's universal law of gravitation, according to this, what are the things which are going to come? So we'll say F is equals to G M naught upon all the distance R square. So as per Newton's universal law of gravitation, force must be this. Okay, force must be this. So remember, if I'm dividing or if I'm doing the multiplication of 1 by m naught on both the sides, so what will come? F by m naught G, this m naught and that m naught will get cancelled, R square. So you will define this gravitational field intensity at m naught mass position Suppose this is a particular location, m naught mass is present there at the periphery. At m naught point location, for whose gravitational field intensity? Earth's, that is the capital M mass. Students, viewers, this is only what? Acceleration due to gravity. So we'll say G, which is basically acceleration due to gravity. Remember, the ideal value is 9.8 meter per second square. We approximate for the ease of solving the numericals as per the students or teachers' convenience as 10 meter per second square. Okay, please note it down fast. Okay, so I hope you have noted this down. There was some issues in the, few have comments that it's not visible here. So I need to increase the intensity of the color. Okay, so now let's understand that how this expression that is G. See, one more thing. We know now that G sorry. We know this acceleration due to gravity expression G is basically G m upon R square. Okay, this is G m upon R square. We can also write this expression in the form of density. We know this thing, Earth is, we'll treat Earth as, it's like oval shape, but we treat it as like what sphere. Okay, so I'll write density is equals to mass upon volume. Volume is, for sphere, it's r cube. So now the mass goes as density 4 upon 3 pi r cube. Okay. When I substitute this here, g, which is acceleration due to gravity, is g. This is rho, and this is 4 upon 3 pi r cube upon r square. If you see the values of this, we can solve this too. G, which is acceleration due to gravity, comes out to be what? This is g rho 4 by 3 pi r k. So this is one of the things. You can also remember this also. Okay. Was not that easy. Okay, so now we'll discuss some major important things. What are these major important things? Let's check it out. G, which is having the ideal value as 9.8 meter per second square or 10 meter per second square. What do you think? Is it same everywhere? Yes, of course, it's same everywhere, but for a particular range. I mean, if your mass is having the height from the Earth's surface, which is greater than the radius, G value changes. Or else, if your mass is at the depth, I mean, if you are taking the mass underground and then you're measuring the G value, it changes. Also, due to the rotation of the Earth, G value changes. When I'm saying G, it means small g, that is acceleration due to gravity. So for the height above the Earth's surface, acceleration due to gravity, small value g changes. At the depth, it changes. For the rotation, it changes. And also, shape of the Earth, it changes. Now you'll think, what is this? I mean, does the shape changes months wise, spring, autumn, and like no. It's just a visualized case, okay, to solve the physics problems. So we conclude like this. Variation of G, acceleration due to gravity. At first, as per the discussion, we'll see with the height how it changes. Okay. So suppose you are having the Earth. This is our Earth. Just imagine, visualize. And for height greater than the radius. And that's the radius of the Earth. Suppose I'm having a mass m0. From the center, it's h, height above. Okay. Hold on 1 second. It means basically from the Earth's periphery, the mass, you can think like this. See, it's a common sense, it's a logical thing. We all are standing on the Earth's surface. We're not at the center. You know, at the center, it's core, crust, and mantle, all those things. It's so we can't go inside. I mean, you know, there is something very much high temperature at its core. So we are at the periphery. At the periphery, if I go up at a particular height, which is basically greater than r, it's a good level height. Okay. So now if we write the expression as per the Newton's universal law of gravitation or universal Newton's law of gravitation, what will we write? We'll say force on this. You know, there will be attraction. We know there will be attraction on this due to which it falls down. Actually, it's acceleration due to gravity, but it changes. We'll see the expression now. For this also, there is attraction, but mass is so heavy, nothing going to happen. So it's a diminished effect on this Earth, on our Earth. Okay. So we'll say G mass is what? Let's treat the mass of the Earth as capital M. There's a particular value, 6 into 10 is to power. You know, somewhere it's like 24, 4. So we'll check it out. Check out the values. No worries in that. First, just generate the generalized expression. Okay. This is G M naught. Now, if you see, whenever I'm taking the distance, Earth is treated as like what? Solid sphere. Solid sphere means from the center. From the center, the total distance is r plus h. So surface up to here it is h. But from surface to the center of the earth, it is what? It is r. So the total is h plus r square. So we'll say force is equals to, let's take few things common here. Let's take r common. Now remember, if I divide both of the sides by m naught, this will cancel automatically. You know the reason, because I've divided it. Okay, let me write it here. It's cancelled. This is again a generalized acceleration due to gravity. This is generalized acceleration due to gravity expression. Now we'll apply here binomial. You know this thing, h is greater than r. If h is greater than r here, if we take it up, what's going to happen? There will be some changes. So when I do binomial expansion, when I take in the numerator, this will be minus 2. So now applying the binomial expansion, we know 1 plus xn. If 1 is very, very greater than this, something as, hold on one thing, there is some error in this. If 1 is very greater than x, so we can write 1 plus nx as binomial expansion. I'm sorry for this. So this, apologies. So you'll write here, because if it goes up, you have to do here binomial expansion application. So for this to be less than 1, the radius must be greater than that. Because if the denominator is greater, this is less, so this will be very less. So I'll say still R dominates. Let me explain you the reason behind this. Why the R is dominating greater than H? Apologies for this. Remember always, there is a gravitational field intensity range of the Earth throughout the space. We will study in the future the expressions like escape velocity. Okay. So if you're not in the range, there's no influence of that Earth's attraction, so you can run away. Very easy it is. So here I will treat R as greater than H. So now what you're going to do is this, just place the values. Okay. So I'll say G dash is equals to G M upon R square. Okay. And this is up expansion 1 minus 2h upon r. You already know this thing that this is simple G value, that is 9.8, or you can take as per your convenience, or A is as 10 meter per second square. This is 1 minus 2h upon radius. This is our expression. Okay, please note it down. Okay, so I hope you have written this thing. Let's proceed next. Now we'll check what happens when we go depth D inside the Earth's surface. Okay, please note it down fast and comment me in the chat box in the Zoom. It will be good if you are on YouTube too, because it is a very A's processing of the video there. Okay, so now let's change few of the things, all of the things basically. Okay, let's start it. So now we have already seen how the acceleration due to gravity expression changes at height h above the Earth's surface. Remember that height must be less than the radius, because you know that mathematically, if that height is greater than the radius, it basically means this, that you are on the surge of going outside of the Earth's gravitational